Well, we're ready to hit the big idea for this unit. In 8.2, we're going to be talking about the Pythagorean Theorem. So the I can statement is I can understand and use the Pythagorean theorem. So Pythagorean, that's kind of phonetically pronounced there. And so we usually just say Pythagorean theorem. Kind of sounds like there's an A there, Pythagorean theorem. So we're going to talk about the Pythagorean theorem, where it comes from, how it's used. We'll introduce that today, but we've got to be really good at working with squares and square roots in order to do well with the Pythagorean theorem. So as a quick review, we talked about this in the last section. 3 squared would be 3 times 3, so that's 9. 4 squared would be 16. 5 squared would be 25. Again, if you've got these memorized, you can just rattle these off and write them down right away. 15 squared, remember, is 225. If we take the square root of 36, the whole idea here is that we're changing a pair of factors into one factor on the outside. This is a pair of sixes. We squared 6 to get 36, so when we undo that process by taking a square root, we end up with a 6 right here. Square root of 27, not quite as nice a number, so we'll do 3 times 9. And again, this should ring a bell. We've got a pair of 3s, so we're going to put a 3 on the outside. Nothing to pair that one up, so that would be 3 radical 3. Let's see, we've got 2 times 27. And if you already know what this one is right here, it's already 3 3s. So here's what we've got. We've got a 2, we've got a 3 times a 3 times a 3. There's 2 times 27. Pair of 3s, so there's a 3 on the outside and then a 2 times a 3 stuck on the inside. So that's going to be a 6, all right? And then let's see. We've got square root of 64. Remember, that's a pair of 8s. That's 8 squared, so we've got our answer right there. And then the square root of 225. You'll notice right up above we took 15 and we squared it and we got 225. So if we take the square root of 225, we should get right back where we started. We should get right back to 15. If you wanted to do the problem like this, the cool thing is it works out either way. This is $2.25 would be 9 quarters. So this is 9 times 25. That's a 3 times a 3. That's a 5 times a 5. And if we put a square root over that, there's a pair of 3s, there's a pair of 5s. So we'd have a 3 and a 5 on the outside. Those would multiply to be 15, so we're all set to go. So today what we're going to do is we're going to memorize and learn how to use one of the most famous and useful theorems in all of mathematics. And it's called this because it's named after the guy who discovered it. And his name was Pythagoras. Pythagoras. So we call it the Pythagorean theorem. And he lived in Greece about 2,500 years ago. Now, Pythagoras discovered a whole bunch of things, but the theorem of Pythagoras, as it's sometimes called, probably one of the most famous things that he did. And almost everybody who's taken a math class remembers this theorem. They remember being taught this. They remember what it is. They may not remember how to use it, but they do remember the theorem. And we'll prove how famous it is, and we'll also talk about why it works the way it does a little bit later. So let's write this down one more time. The Pythagorean theorem, Pythagorean theorem, relates the sides of a right triangle. So what I'd like you to do is I'd like you to circle the word right. It's got to be a right triangle. The Pythagorean theorem only works with right triangles. So in order to use the Pythagorean theorem, we've also got to be familiar with the vocabulary that we're going to use with right triangles and with the Pythagorean theorem. So a right triangle has a right angle. So you'll notice we've got a diagram over here. In this little box, we've talked about this before. That means that that's a right angle. The side across from the right angle is called the hypotenuse. H-Y, hypotenuse. The hypotenuse. So this side over here is the hypotenuse, and I usually abbreviate this with HYP. If you'd like to do that, that would be just fine. So the hypotenuse is across from the right angle, and the hypotenuse is always the longest side on the triangle, and you might think about why that is. So if this is a 90-degree angle right here, there's only 180 degrees in a triangle altogether. So if we've used 90 of them here, these two angles have to split the remaining 90 degrees. So these are going to be smaller angles. And in geometry, there's a concept that says the larger the angle, the larger the side that's opposite. Or sometimes I'll say the bigger an angle is, the bigger side it cuts. Bigger angles cut bigger sides, smaller angles cut smaller sides. So these other sides over here are definitely going to be smaller than this one right here. And we're going to say it's the biggest angle. Okay? So it's across from the biggest angle. And the two shorter sides, they have a special name. Well, sort of. They're just called legs. All right. So this is the hypotenuse, this over here is a leg, and this over here is a leg. It doesn't really matter, which is which or anything like that. There's nothing special about the two of those. We just call them legs. And then we use some letters to represent these legs. So this is A, B, and C. Now it's important that you pay attention to this. A and B are going to represent the legs. And it doesn't matter whether I call this one A or this one A. I could do AB here or AB here. It doesn't make any difference. The important thing is that A and B represent the legs, the two short sides. And then C is the hypotenuse. So I'm just going to draw this. These two are the legs, no particular order. And this one right here has to be the longest side. It's going to be the hypotenuse. All right, so here's the theorem, and this theorem only applies to right triangles. So we're going to write that one more time. It only applies to right triangles. So here it is. So the sum, we'll write the word sum right here, the sum of the squares of the two legs is equal to the square of the hypotenuse. We're going to write that again. Good practice here, hypotenuse. So the sum of the squares of the two legs is equal to the square of the hypotenuse. And normally we remember it just with this little formula, this little equation. And the equation is this. We're going to take this leg and we're going to square it. So that's going to be a squared. And we're going to take that leg and we're going to square it. That's going to be b squared. And sum means we add these together. So the sum of the squares of the legs, so we square the legs and add them together, and it's equal to the square of the hypotenuse. So the hypotenuse is c, and we're going to square that. So the theorem is a squared plus b squared equals c squared, as long as we're dealing with a right triangle, and as long as a and b are the legs of that right triangle, and c is the hypotenuse of that right triangle. Now, there are tons of people that remember this theorem, as we're going to prove a little bit later, but they can't remember what the parts are called. So I would much rather than having you memorize this, I'd rather have you to think of the Pythagorean theorem this way. Please think of it as leg squared plus leg squared equals hypotenuse squared. If you do that, if you know you're working with a right triangle and it's always leg squared plus leg squared equals hypotenuse squared, it's not going to matter what sides they give you. It's not going to matter whether they change the variables on you or something like that, like say they use x, y, and z rather than a, b, c or something. You're always going to be able to do this. So please think leg squared plus leg squared equals hypotenuse squared. So we're going to go ahead and take a look at a couple problems and we'll apply this idea. So on this problem A right here, in example number 1, we have a 4, we've got a 3, we've got the right angle right here, so what's missing is the hypotenuse. Now you could choose any letter that you want. I'm going to usually stick with the A, B, and C unless they give us something else. So I'm going to put a C right here, and then just for the heck of it, let's call this one A and let's call this one B. Now I could think of this as A squared plus B squared equals C squared, and then plug in the pieces that I've got and then solve for the missing piece. But I'd much rather have you think of it this way. Let's do leg squared. So the leg is 4, let's square it, plus leg squared, the leg is 3, let's square it, equals the hypotenuse. Let's go find what we're using to represent the hypotenuse, and let's square that. Now you'll notice that we've got all numbers on this side, a variable over here. So the variable term is isolated, but let's go ahead and simplify here. This is a 16 and this is a 9, and you can see why it's so useful to have those memorized. It goes very quickly, we don't have to reach for a calculator. This is going to be 25 over here equals c squared, and then we need to undo the square on the c, so we're going to take the square root of both sides. Now normally when we do that, we put a plus or minus 5 and then we'd circle the answer. My question for you is, because we're dealing with a triangle, do we need the plus and the minus? Okay, we're going to write do not need, need the plus minus. Okay, it's only positive because it's the length of a side. So it is the length of a side. And lengths are always going to be positive, okay, of a side. So we don't need the plus or minus. All we just need is the plus. In fact, if it's just positive, we don't need that at all. So here's what we've got. If one of the legs is 3, the other leg is 4, then the hypotenuse has got to be 5, and we're all set to go. So I'm going to draw a line right here, switch colors, and then come back over here and take a look at this. Again, I'd prefer you not think just a squared plus b squared equals c squared. I'd like you to think, what am I missing here? Am I missing a leg or a hypotenuse? I'm missing a leg, so I'm going to call that a. So we're going to do leg squared plus leg squared equals hypotenuse squared. So this is going to be a squared, And this is where it's helpful to have some of these memorized or have some idea what's going on here. These numbers are a little bit bigger than the ones we had memorized, so we're going to grab the calculator. We are going to do 24 and we're going to square that. So we get 576, and before I get rid of the calculator, let's go ahead and do 25 squared. It's got to be a little bigger than that, so it's going to be 625. So I get 576 and 625. So 576 and 625. We're going to subtract 576, bring up the calculator here. Let's see what we get. I'm just going to hit minus because it's going to know that we're using that last number as the answer. Minus 576. Hit enter and we get 49. So this is good news. A squared equals 49. We're going to take the square root of both sides. This is one that we recognize, so this is a 7 and we're all done. So A equals 7 on that particular one. Let's do another one. Numbers are a little bit bigger here. Again, you'll notice that on this particular problem they labeled this side as x. We don't have an x in the formula, but we do understand, this is why it's useful to think of leg squared plus leg squared equals hypotenuse squared. What we're missing right here has to be a leg because this is the right angle. That's got to be the hypotenuse. So we're going to write this down this way. We're going to do leg squared plus leg squared equals hypotenuse squared. And gosh, 24 squared, we used that just a second ago. So this is going to be x squared equal, or x squared plus 576. And then 40 squared, we'll throw that into the calculator in just a second, but 4 squared would be 16. And think about that when we type in 40 squared, 1600, because we've got the 4 times 4 makes the 16, and then we've got the 2 zeros to add on there. So that's going to be 1600. Again, we'll have the calculator do the heavy lifting here. We're going to subtract 576 from both sides, and we get 1024. So we get x squared equals 1024, and I'm hoping that looks familiar there. Square root of 1024, we did that I think yesterday. That is a 32, so we're going to circle that. Again, I wouldn't just rely on your head to do that. Let's double check on the calculator, especially if this were a test. We'll type in square root of 1024, hop outside, hit enter, and there's our 32. So we are all set to go. We got that one right. Okay, let's keep looking at this right here, and if you look at the next one, this looks horrible. This looks absolutely awful. But I think once we get used to this, you'll find that these are actually pretty darn easy. Again, notice that we've got the right angle right here, so we're missing the hypotenuse. So let's do a leg, square root of 6 squared, plus a leg, square root of 15. We'll square that. Notice I've got each leg in parentheses, and I'm going to square that, equals the square of the hypotenuse. Leg squared plus leg squared equals hypotenuse squared. Now here's the cool thing about this. This means we're going to do the square root of 6 times the square root of 6. So we're going to write it like that. Remember that property of radicals that says if you've got a product of radicals, you can do the radical of the product, so we can multiply those together. Well, look at that. There's a pair of 6's. So when you square a square root, notice that we still get a 6. All these do is these undo each other. Whatever the square root did to 6, the squaring undoes that, so this is a 6. And guess what this is? If we square the square root of 15, we get 15. Okay, those operations undo each other, and then over on this side we have an x squared. So this is 21 equals x squared. We'll finish this off by taking the square root of both sides. We get an x on this side, and again, we don't have to put a plus or minus on there. It's just, whoops, the square root of 21. We're going to circle that and we're all set to go. So you don't even need a calculator for this, even though these look like they're really ugly numbers to work with. This cool operation here where we undo the square root with squaring, the fact that they're inverse of each other, really cool that you can do that. Okay, let's take a look at this next one. There's no label for this missing part, but let's see what we get here. Let's see, we've got a 4 for a leg, and we're missing a leg right here. So I'm going to go ahead and use B just for the heck of it. Ooh, I am going to change colors here, though, so that's going to be a B. So we're going to do leg squared plus leg squared equals hypotenuse squared. And I'm hoping these are things that you do not need a calculator for. So this is going to be a 64. Again, that's where the value of memorizing all those perfect squares comes in. We're going to subtract 16. So we get b squared equals, this would be 48. And then we need to take the square root of both sides. Now, 48 is not a perfect square. 49 is a perfect square of 7. But this is going to be a little bit smaller than that. So a couple things that we could do if you wanted to break this down like this. That's a 4, which is a 2 and a 2. and a 2 and a 3. So take a look here. We've got 1, 2, 3, 4, 4 2's and then a 3. So this would be b equals the square root of a 2 times a 2 times a 2 times a 2 times a 3. Pair of 2's, pair of 2's. And again, if you can see that right here and simplify it more quickly, that's totally okay. You're going to have 2 2's on the outside, which would be 4, and then a 3 stuck underneath. So we'll go ahead and circle that. And then let's take a look at these last couple right here. There's no diagram on these, and we can deal with that, but it makes it even more important that you pay attention to how this is noted. This is a equals 12 and b equals 8. That means these are the legs, and that's just standard operating procedure. If we've got an a and a b in a Pythagorean theorem problem, in a right triangle problem, those are going to be the legs. So this is going to be leg squared plus leg squared equals hypotenuse squared. This is going to be 144 plus 64. Again, we can do that much without a calculator, and I think we get 208 here, but let's grab the calculator and just make sure. So let's do 144 plus 64. We get 208. Okay, now I'm going to clear this off. I'm going to take 208. That is not a perfect square. That's not on our list. So I'm going to take the calculator and we're going to go ahead and do this. Because it's even, I'm going to hit divide by 2, kind of that technique we did before. So we divided by once and we got 104. Okay, divided again. We're going to get 52. Divided again. We're going to get 26. So we've divided 3 times by 2 and we get a 26. This is still even. So if I divide by 2 again, I end up with 13. So here's what we get. When we take the square root of both of these, this is going to be a 2, a 2, a 2, and a 2, and a 13. Okay, so let's just go back and double check. Remember, it was 208 before, so we divided once and got 104, divided again and got 52, so we divided by 4 2's, there they are, and we ended up with 13. So here are all the common factors. So if we take out pairs of 2's, we end up with this. We end up with a 4 on the outside and a 13 on the inside. And then we're done with that. Now, as ugly as this last one looks, I want you to take a look at it. Again, we've got B and we've got C, so what we're missing is a leg. So I'm going to do leg squared, whoops, change colors here. I'm going to do leg squared plus leg squared equals hypotenuse squared. And again, it's just a good habit to get in of putting parentheses around those. So this is a squared plus 25. And that's a perfect square. And then with this, all we're relying on is the fact that squaring is the inverse of taking a square root. These two operations are inverses of each other, so whatever the square root did to 26, the squaring is going to undo that. So that's going to be a 26 over here. Look how nice this is to solve. We're just going to subtract 25. So we get a squared equals 1 and take the square root, and we get a equals 1. So as ugly as that number was, we end up with a really nice answer here. Now I'm going to flip the page over and I'd like you to do the same. There are lots of proofs of why the Pythagorean theorem works the way it does, and you kind of have to find one that kind of makes sense to you. I'm going to point out a couple of these. In fact, I would highly encourage you to type these into a browser here. There are so many proofs. Even our 20th president, President Garfield, he found a proof of the Pythagorean theorem. So I'm going to show you one that's pretty convincing. This is the water example. So I'm going to pull that up. We're going to take a quick look at it. Okay, now the cool thing about this, I'm going to pause this for just a second. The cool thing about this is it doesn't require any talking or anything. You can visually see what's going on, but let me just set this up a little bit. What we have here is we've got a wheel. They're going to spin this in just a second, and they've got a solid triangle in the middle here. That triangle happens to be a right triangle. You can see this right here. And what they've done is they've made a square off the side of this triangle that has the length of this is exactly the same as the side of the triangle. So if this was 5 centimeters, this would be 5 centimeters. This is a square right here, and it's actually filled with some colored water right here. They've done the same thing over here off this leg. They've made a square based on the size of this leg, and it's full of colored water here. So this is literally a leg squared. This volume of water is a leg squared, and this volume of water is the other leg squared. So if we put these two legs together, that would be a leg squared plus a leg squared. Now what they're going to do, I'm going to go ahead and play this. What they're going to do is they're going to rotate it, and you'll notice what happens is the water starts sloshing out of this square and this square, and it starts filling this up. So we've got a leg squared here, we've got a leg squared here. It's going to dump all of the water in here and take a good look. Once the water's empty of the two squared legs, it fills up the hypotenuse squared. They're going to then rotate it around the other way, and you'll notice that the hypotenuse squared is going to exactly dump back into these two squared legs. So it's a pretty cool visual, and there are lots of others. I would really encourage you to look some of those up. So I'm going to get rid of that, and we're going to come back here. I've got two that they're pretty good. You could just Google or type into YouTube, proof of the Pythagorean theorem. You'd see a bunch of different ones. I like both of these other ones, but the water example is pretty easy to follow. I would like to challenge you to do something. Go home and ask an older brother, sister, mom, dad, aunt, uncle, neighbor, something like that. See if they can complete this sentence. A squared plus b squared equals. Most all of them will get it right. They may not know that it's the Pythagorean theorem. They may not remember how to do it or how to use it, but they will remember it. So it is something that you'll remember. I would, again, much rather have you think, 20 years from now, leg squared plus leg squared equals hypotenuse squared, because that's a little bit more descriptive than a squared plus b squared equals c squared. All right, good luck on the assignment.